Swayam Prabha. Digital India. Educated India.
Today we will be seeing the experiment of corrosion of aluminum in two different media. One is in NaCl, that is seawater media, 3.5% NaCl, and another is NaOH media. So basically we will first look at the properties of aluminum, its corrosion resistance and its corrosion behavior, and then move on to how the experiment works and how to set up the experiment. So here we have the aluminum reduction potential, it's minus 1.66 volts. So in comparison with say iron, it should actually be corroding more in comparison, but aluminum doesn't corrode that much. That is because of spontaneous passivation. There is a adherent oxide layer that forms on top of aluminum. That alumina is actually 4 to 5 nanometers in size, and that alumina protects the aluminum from further corrosion. So you can see here, basically there are 4 regions. So one is basically the aluminum immune region that occurs at a very low voltage at around minus 2.5 volts, and the others, you can see that here aluminum dissolution occurs at a low pH below 3, and above 9 also there is a corrosion, and this alkaline corrosion is very vigorous. Right. So what happens in this passivity? So this passive region is basically because of the formation of the of Al2O3, and that Al2O3 formation can also be tuned. Right. So we will see how Al corrodes in NaCl first, then we will set up an experiment on in NaOH, then we will move on to anodization or a surface modification of aluminum. Right. So we will move to the experimental part of checking how the corrosion of aluminum is in seawater. Right. Yeah. So this is basically a typical potentiodynamic polarization curve of aluminum in seawater. So there basically how a potentiodynamic polarization curve looks is, we need to first see what are the axes. Basically the axis is current versus voltage, and the current is plotted in a logarithmic scale. Right. And we can see that so basically before any corrosion experiment we need to stabilize the electrode electrolyte system. So basically there will be a typical, say in NaCl we have seen that this is the open circuit potential in NaCl. Basically what exactly is an open circuit potential is when there is when it's just dipped inside a solution and there is no current involved. So basically we can see that this is the potential of potential in open circuit. And this potential, as you can see in the Pourbaix diagram, that this is basically from the Pourbaix diagram and this OCP, we will be able to correlate that the aluminum is actually aluminum is stable and it doesn't corrode in this medium as such. So to understand its behavior across potentials, we perform a potentiodynamic polarization. This open circuit potential stabilization is typically done in hours. So post that stabilization, we start off with performing potentiodynamic polarization. So what exactly is potentiodynamic polarization? So basically around the we need to understand the behavior of aluminum around the open circuit potential. So near the open circuit potential only its variation will be most seen in natural environments. So basically we move from here, I have set it for at a very high range from minus 1.5 volts to 0.6 volts. So how the corrosion current varies, we can see that here. So basically this is basically the cathodic region. So it's because it's below the open circuit potential, this is the cathodic region. So cathodic region in the sense it does not corrode in this, and you can see that the current is also not that high. So we can see that the current is in milliamperes range, and once it crosses the corrosion potential, this region here around minus 1 volts is basically the corrosion potential of the system. So basically we'll be able to understand the corrosion dynamics using this potential dynamic polarization. So post this, it enters into the anodic or aluminum dissolution regime. So what happens here, we'll be able to see it. So for example, this is in aluminum is corroding in NaCl solution, and we had seen that it forms a passive film. So that because of the presence and the formation of passive film, we can see that the current is very low. You can see that it's around in microamperes, right? So what happens here? So there is a very high buildup of current with minimal change in potential. Why does this happen? Is because of the presence of chloride ions. Chloride ions are very aggressive, and they are able to penetrate through the oxide film environment, and this causes a sudden increase in the current, and the current increase keeps increasing, and it reaches a saturation around 0.01. But this is actually not a saturation. So why you would not call this a saturation is because this is basically this current is limited by the potentiostats limitations, right? The actual current, if you measure using a different route, say a multimeter or another equipment, we will be able to measure even higher currents. So once the voltage here also reaches around minus 0.5, or say something like around here, minus 0.5 to 0, we will be able to see vigorous hydrogen evolution reaction occurring on the graphite electrode here. So here we can see that there is a 3 electrode system. We will replicate this system in the NaOH solution also. I will set it up, and we will be able to understand how it corrodes in NaOH. Right? So this is basically a corrosion cell. So this corrosion cell has almost a volume of around 150 ml, and we will be able to set up 3 electrodes, and the electrode that is going to be set up for corrosion will be set near here, and we will be able to insert the reference and counter electrodes. So we will set that up, we will pour the solution in and set the fix the electrodes. So basically this is an NaOH 0.1 molar NaOH solution. So basically this is the reference electrode. Probably this reference electrode is calomel electrode, and this reference electrode is basically made of mercurous chloride, and the counter electrode is graphite. So the counter electrode can be graphite or platinum. Platinum basically in hydrogen evolution reaction. So the counter reaction in corrosion reactions is generally hydrogen evolution reaction, and platinum has very low over potential for hydrogen evolution reaction. So platinum is preferred, but in this case we will use a graphite also. Graphite is equally good, but platinum is the best for hydrogen evolution reaction. So we will insert platinum as well as the calomel electrode. So this is the working electrode. So we saw that the pour by diagram here, and we could see that here we are in NaCl we are mostly in the passive region of 3, and it's basically Al2O3 formation. But when we go to NaOH environment, we are you can see that for a wide region of potential and pH above 9, we are basically in the dissolution region, and this dissolution will be very aggressive, and this is what happens when we immerse it in an NaOH medium versus an NaCl medium. So this shows that environment is also equally important when it comes to corrosion. So what the the next part here is basically surface oxide formation and its modification, so that aluminum can be used for a variety of purposes. So how that is done is basically through a process called anodization. So anodization, it can either be barrier layer anodization or porous layer formation. So the barrier layer formation is performed using a process called hard anodization, where the voltage is very high, and in the porous AO formation, we have a mild anodization occurring through a process of immersing the aluminum in acidic media and supplying a voltage of around 40 to 50 volts. So, and using this porous aluminum oxide, we will be able to synthesize nanostructures and also perform sealing and for decorative purposes. So here also the metal dissolution reaction is the anodic reaction, and the cathode reaction here is hydrogen evolution reaction.